Hi, my name is Sunny Bains, and I'm going to talk about TiDB. How many here have heard of TiDB? Nobody, okay. After this, 100%, I suppose. Okay, so TiDB is a distributed SQL database, and I'm going to talk about how TiDB manages, what it means when we say modernized data management. So it does many things to achieve this, but the two, for brevity, I will talk about how you can manage multi-tenancy, for example, in large deployments, and how it scales storage. These are the two things I will stress upon. There's many other things which anyone can ask me questions afterwards. Happy to answer. Don't feel shy. So I will focus on these two things, a little bit of the history. So we can skip this slide. These are some of our existing customers. We can skip this. So I'll talk a little bit about the history, the evolution of the architecture, some parts of what make up the components, of a little bit about details about some of the components. Then we will eventually move on to how it's still evolving and how we have another offering which is called TiDB Serverless. This is cloud specific. I'll talk in detail about that. And then the part that I mentioned, how we manage multi-tenancy. So the multi-tenancy part applies both to serverless and to our on-prem offering. It's all open source, so that's, if you want to look at the code or you're interested in distributed systems, distributed databases, knock yourself out. It's all on GitHub. So a little bit of history. The founders of TiDB were working for a large internet company, and they were growing like crazy. So they were the best of times, but the databases weren't scaling. They were big MySQL users at that time, and MySQL was, in fact, one of the most popular databases then, and it is now. It was used very extensively, and in order to grow, they had to constantly manually shard and reshard. So one of the problems that they faced when they started sharding was the developers now had to start adding sharding keys. So that added complexity to their applications. So now, sometimes they would forget to add the shard keys, and that would cause problems in their applications. And resharding, as the data was growing almost exponentially, resharding became extremely painful. And that pain, more or less, has continued until a new architecture sort of came about, which was Google Spanner. Google Spanner architecture was meant to address the sharding problem. So it automatically shards for you. You don't have to remember the sharding key. You don't have to manually shard and reshard. It all works for you automatically. So the big thing that, I won't go into detail, but the big thing there was, rather than shard the nodes and partition within the nodes, they would, Spanner replicates the pages. So imagine you horizontally split your table, and each region in that table is replicated using some kind of consensus protocol. So there are many variations, implementations. Spanner is a reference in some way. There is Yugabyte, there is TiDB, and there is CockroachDB. The CockroachDB and Yugabyte are Postgres, and we are MySQL compatible. That's our main thing. So I won't go into detail, you can read about it. So there's a problem. It's proprietary, it's not open source, and we are big believers in open source. And it requires special hardware, two-time. And this is by design. TiDB is designed to run on commodity hardware. It is a deliberate decision. We do not like to run on specialized networking hardware or RDMA or whatever. This is one other requirement we've set for ourselves. Also, Spanner has a specialized proprietary API. It's not standard SQL. They have some thing, Postgres, half-hour Postgres protocol, but I won't go into that. So this is our design philosophy. It's a shared nothing architecture. Developers should not be concerned with shard details. This is something we considered very important. This has come from the experience of the founders. And I've met many customers and users, and this is something they don't want to deal with. But something that TiDB can do, which I won't talk about in this talk, is that developers should also have the flexibility to control data placement. So now, if imagine you've got your data is spread out over your cluster. It could be you want to specify should it go on a certain rack, certain data center, perhaps different region. TiDB has the facility via SQL which allows you to place your data wherever you like. It has that flexibility. I won't go into that detail. We use standard SQL, and the optimizer should determine how to do the distributed query execution. It should not be the job of the application developer on which chart to go to, what to do. Distributed transactions, and the key point here is we would like to support strong consistency guarantees out of the box. This makes application developers like during the phase when data was growing very fast, 2008 to 2015, there was a fashion of weakening the consistency, and that's where all these key value stores became very popular. There was no other solution at that time. So in order to scale, there was a tendency to weaken the consistency. Because we can scale easily, we would like to guarantee a strong consistency. So that's a very key point for us. We would also like flexible read consistency policies. So it's related to the first point. It should be highly available, but not at the cost of strong consistency. So you've noticed we mentioned consistency several times. We think it's very important for any distributed database. No compromises. So this is how it started. We initially wrote a simple SQL parser and optimizer. 0.1, it didn't go too far. Then we settled on RocksDB as a storage engine, and we layered a raft protocol, consensus protocol on top of it. So this eventually became what's called the TiKV, distributed storage engine. It uses raft. It has something called a coprocessor, which is a query push down. In a distributed system, you don't want to fetch individual rows from your storage, because that increases network I/O. It produces a lot of latency. So you want to push the query down to the storage so it works closer to where the data is. So the optimizer in TiDB will create a DAG, a directed acyclic graph, and push it down to nodes will work closer to the data. Let's say you do a select count star as a simple example, and your data is across all three. So then each of those nodes will give you a select count star of the data that you've got. So then in parallel, they'll do a select count star, send 3 results back to the query optimizer, which will just simply add them up and send them off to the client. So these are some of the powerful things you can do with a distributed storage engine. So this is our canonical architecture. I'll spend a little bit of time sort of hand waving here. So the brain of a TiDB cluster is on the right hand side, PD. So PD is the metadata server. So PD stands for placement driver. I'll get to that in a little bit. There is the SQL layer. You can ignore the TiSpark. So that is the SQL front end, which supports the MySQL protocol and has the MySQL and also has the SQL optimizer. These are the storage nodes. So let me try and explain what those little arrows mean and how it's supposed to work. So think of the region 1, region 2, region 3 as your horizontal partitioning of a table. So let's assume they're all part of region 1. This color is part of one table. Region 2 is also part of the same table, and let's say where's region 3. Now, you will notice that we have 4 nodes, and the regions are spread out across the nodes for high availability. One of them will be the leader, and the others will be followers. And each of these regions is a separate raft group. So raft is the consensus protocol. And by spreading it out, we increase the chances of a single node taking down the cluster, for example. So as an extreme example, let's say node 4 goes down, right? And so let's say that was the leader. It will do an election, select a leader among these two, and still continue operation. Region 2 will be affected. It will do an election on that group and then carry on. Region 3 is not affected at all.
So that's how it's supposed to help. TiFlash is our column store. It is an optional component. TiKV is the critical component. So I'll get to how it's used by the optimizer later on in the talk. So now let's switch to PD. PD is the brains of the whole thing. So once the data is spread out, the TiDB SQL server has to locate that data somehow. How does it do it? It talks to PD. Now PD and TiDB are stateless. So where is that data stored? PD runs a separate etcd cluster storing the metadata. So it's completely separate from this cluster. So TiDB will pass the query. It'll ask PD, okay, these are the regions I'm interested in, or these are the pages or whatever. It does the translation. It says you need to go and look for region 4 on leader on node 1, region 2 leader on, let's say, node 4, and let's say those are the two ones. So then it'll go and talk to those and do parallel fetch and pass down any DAG that's required for the query. So this is roughly what a PD sort of does. It also monitors the state of the system by listening for heartbeats, because it has the distributed system. The classic thing is, how do you tell the difference between a node that is down and a node that is slow? You can't. So there has to be a timeout. So if a node doesn't, if PD does not detect a heartbeat within a certain amount of time, it assumes that the node has gone down, and whichever regions were on that node, which were leaders, if they were only leaders, then it will start a raft election process on the remaining nodes. But if it was a follower, if let's assume node 4 went down and there were only followers, there is no need to do anything, you can move on as normal. But only if there was a leader on that, only that leader's followers have to then now elect a new leader, and then once that's done, then it can proceed. But the rest, let's say the rest of your load is looking at tables that were not located on node 4. They will carry on regardless. They have no idea that some node has gone down. So these are the advantages that it has. So this is like a high level view of how the parser, optimizer, and then how it goes and fetches stuff. You can, for time, we'll skip this. This is important. So the flash, which is the column store, unlike, I haven't seen any other solution personally, so I think this is unique to TiDB. TiDB's column store and key store are strongly consistent. What's the advantage? Advantage is that if you have a query like that, the optimizer can send a fragment of the query to, let's say it's a table scan, it can send it to column store, and any other range scan that it has to do, it can do it from TiKV. I don't know of any other database that actually can do this. For example, if you have Alloy DB, it's eventually consistent. You can't do the same statement. If you have HeatWave, it can't do it. It's eventually consistent. You can only do it if it's strongly consistent. So it can even do a partial fragment of a query across column store where it makes sense to do it. I think this is extremely important for large queries. So this is like a general thing. The core capability, it's scalable, it's elastic, it's highly available, it's multi-region. You can ask me the details later. We have some other experts here, you can ask them too, because they have more operational experience than I do. You can place data wherever you like. I will go into detail about resource control, about keys, what key space is, and PD can scale independently, so it's multi-tenancy. So these are some of our customers, and this is public information. So I just sort of gathered some of their blogs. So these are some of the benefits that they got out of switching to TiDB from other databases. You can read for yourself. I mean, it simplified their architecture. They got strong consistency, very important according to me. They saw a huge reduction in latency, especially the P99, which is what really in production people actually care about. And it scales extremely well. So this is a very interesting case. So this is from a very older version of TiDB, from about 4 or 5 years ago. They were inserting in one of our older versions 100 billion rows per month and growing at 30%. So you can sort of do the math and see compound it and see what they're probably doing now. And the reason they switched is why most people switch. Sharding is painful. If you haven't done sharding at scale, consider yourself lucky. You haven't felt the pain. Upgrades are easy, does rolling upgrades. DDL on large databases is even more painful. TiDB has an excellent DDL story. Sadly, I don't have the time to explain the details, but it does. It uses the F1 online schema change algorithm. It can do, in one of our tests, 10 terabytes in like 40 minutes, a create index. It's pretty good. So this is Flipkart. They wrote a blog, one of the most popular blogs actually that we see. So it can do 1 million read writes per second. So I'll be publishing the slides. I won't go over the details so you can read them. So it's pretty impressive stuff. I mean, I've worked with databases for a long time. It's pretty impressive. So now I'll talk about how we are still evolving and how we also have another thing called TiDB Serverless. So what are the new architecture goals? Multi-tenancy. So multi-tenancy could mean anything, but for us it is, or for users, it's usually, you want to, let's say you have 10 applications in your production center, and you have 10 different databases. You want to reduce your operational cost. So you want to say, okay, can I run all this on 2 clusters or 1 cluster? So the common problem that people have is, how do you isolate the different applications from each other? I'll go into some detail later. And that's where handling multi-tenancy becomes important. So the other thing these days is the cloud is everywhere, and they've solved some really hard problems for us. And we want to make use of that infrastructure. So if we were to create something like S3, for example, it's a huge project. Doesn't make sense. S3, for example, gives some great guarantees. It has some good things, it has some bad things. It's cheap, but it charges you a number of requests. So how do you optimize for all those things? I'll go into some detail there. So you want to leverage cloud's elasticity and scalability. You want to leverage the HA features that are built in. You want predictable performance. You want to separate the reads and writes, the placement rules. Upgrade scaling is like standard. And faster startup time is also important for serverless type of applications, and so I'll go into some detail there. So what are the multi-tenancy requirements? The key ones are, you want data isolation. You don't want the applications. They could be different. Let's say if you're running a service, they could be completely different customers, so you don't want their data to be visible to each other. But assuming you're running your own tenants, you don't want the different tenants impacting each other's SLAs. So in the TiDB serverless architecture, each tenant has a dedicated compute node. So TiDB has a disaggregated compute and storage architecture. So if you're familiar with Amazon, the storage layer is S3, which is the same for everybody, so it is shared. Data is physically isolated by tenant ID. I'll go into that a bit. So this is roughly what it looks like. So how to explain this, let's start from the bottom. All the data ends up on S3, right? How does it get there? It gets there via the protocol, the RAF protocol that's in the TiKV layer. Flash data, TiFlash column store also goes to S3. So you go up, the SQL nodes are at the layer above that. So when a client connects, the gateway looks at the tenant ID and routes the traffic. So that's from where it starts. But the tenant ID goes all the way through the infrastructure to partition what resources are used by that tenant. So that's what it roughly does. So when you have a serverless, you want instances to start up quickly. So you have a pool. You need a configuration layer. You need some way to control that configuration. The pool controller will then decide how many spot instances to keep in the pool. So that if a user says, I want to suddenly fire up 10 different nodes, and you have them in your pool, they're already warm, you just simply, because it's stateless, you simply connect them to your storage nodes and it just instantly starts working. One other big advantage which I forgot to mention is In a shared nothing normal TiDB deployment, let's say you have 3 nodes cluster. You have 3 instances of the data. In serverless, you have only 1 instance because S3 is doing the HA for you. That is what you want to leverage. You want to reduce your cost. So that's a big thing for us. And we actually have reduced the cost of our serverless deployment a lot. Okay, so TiKV, which is the on-prem TiDB storage engine, you can think of that as a distributed RocksDB. Whereas we had some problems, we couldn't leverage S3, and we had some other issues with RocksDB. So we wrote our own LSM storage engine. It's called the Cloud Engine. So one of the things that we found with RocksDB is compaction. And this is like a common LSM problem. Compaction is very painful. So now if I'm storing my LSM on my local disk, let's say, and I run compaction against it, it steals IO and CPU from that node. So the user threads get impacted. It introduces jitter. In this architecture, we can use spot nodes to work directly on S3. So the front traffic is not affected at all. This is a really big thing to avoid jitter in production loads. It gives you very nice predictability. Elasticity, we want to start up compaction or start up some background process seamlessly. Multi-tenancy gives us efficient use of resources. You don't want to have like 20 servers running all the time. It should be on demand. As a customer, you shouldn't have to pay for all the provisioning that you do upfront. Do it on demand. So, and you can pay as you go. As you use whatever resources you use in that period, you pay for that. So that's the other advantage. So we want, as I mentioned, we want to leverage S3 for durability, scalability. We want to reduce the cost. We want to be immune to performance fluctuation. We use remote spot instances for data compaction. This is like a big problem in LSMs. Another thing that we've done is, I mentioned the coprocessor. So in serverless, we can actually fire up spot instances even for coprocessor. Let's say, as an example, we start up completely separate processes that are co-located to near the cache of the, let's say, there's one part I missed. They're co-located with the cache servers. They will take the load of the main TiDB SQL processing or even the storage node and run multiple queries in the same remote coprocessor in a separate node. And they can be scaled independently. So what's the trade-off here? The object store is cheap to store, but the request cost is high. Block storage, EBS, latency is low, and the request cost is none. So how do you make the best of both worlds? So what Serverless and Cloud Engine does is, it uses EBS as a write-through cache. The canonical store is S3, but the local storage could be anything. It could be, we currently use bare metal NVMEs, but it could be, or even EBS, but it could be anything theoretically. So it uses the local infrastructure for cache, and it uses S3 for the canonical store. So by balancing the two, we can give low latency and we can reduce our overall storage cost. So in practice, what usually happens is 85% of your data is usually cold. This is anecdotal. It could be 20, 70, doesn't really matter. And you have only 15 to 20 or 30% of your data that's hot. So your bulk of your data will be in cheaper storage then on S3 by default, simply because of the cache. The hot data will be EBS storage, which is little more expensive, but that's fine because the bulk, or 80%, let's be conservative, 70% of your data is on very cheap storage, at least because we run serverless. It's very cheap for us, very, very cheap. That's the advantage. You get the best of both worlds. So we have a RAF. The RAF part, I think I've mentioned quite a bit. So that's the cache. Those are the S3, our main storage. So that sort of gives a high level view of what it is. I want to go to, let's skip this. I'll skip this part. I think this is very important. This I'll go with. Hopefully I can finish it into, okay, this. So TiDB extends the MySQL SQL syntax. So what does this do? What is this about? So it has an abstraction called a resource unit, and you can create a resource group. Let's say an example would be create resource group, give it a backfill of 1000, and that attribute is burstable. What that means is that for this resource group, any query, any session that's attached to this can use all the resources if required, and if they're free, or if it's that high priority that it will work anyway. You can use standard DDL kind of thing like alter, and you can query whatever the status is. So this resource group you can attach at the user level, session level, and statement level. So what does that mean? So let's say you have some background jobs and you have some foreground jobs, and you have the classic case is that you have lots of short point select queries, and you have some large 5-minute running queries that use a lot of resources, have massive joins. You don't want to impact the short point selects by these very large queries. So how do you do it? It's a very common problem outside of this. By using this, what you can do is you can create a resource group that has a smaller backfill, which is then attached to your long running queries, and you have a higher priority resource group that's perhaps burstable, and you give it to the point selects. Now the point selects will then run at a very high priority. So internally how this works is that the TiKV or the storage side of things, they work in small increments, right? So your long query will not be a runaway query that runs for like 5 minutes and everybody else is stopped because there are no resources. No, it'll give it a little bit of time. Once the RUs run out, it'll be suspended by the scheduler. And then that way the high priority point selects will run at top speed, and the long running query will not impact that. That is extremely important for multi-tenant loads, and that's why I wanted to stress upon this. So you can set up the backfill and you can calibrate it using the syntax. You can ask me later. I wanted to go in detail, but I don't have time. So this is how it actually works. So you have the data stored in PD. That measures the SQL execution time RUs. That measures the storage cost. This is actually a great paper. It implements the mClock algorithm. It came from VMware. I think it's worth reading if you are interested in this sort of thing for scheduling. It's really good. That's what it implements. And I just have 1 minute now. Anyway, so please, I don't have much time. I have to skip some slides. If you have any questions, feel free to ask. Okay, thank you.